You ever stop and wonder how something like GPT actually learns to read? I mean, really read? It's not magic, right? It's all about teaching it an alphabet. And what's wild is that back in 2019, OpenAI published this paper on GPT-2, and tucked inside was this tiny, almost unnoticeable change to that alphabet. A change that turned out to be one of the biggest breakthroughs in AI. Seriously.
So here's the fundamental puzzle for any language AI. Think about it. How do you possibly teach a computer to understand everything? We're talking every word in every language, plus all the emojis and even computer code. You have to somehow take all of that messy, beautiful human stuff and turn it into cold, hard numbers that a machine can actually crunch. It's a massive, massive translation problem.
Okay, so let's dive into the first attempt. The early models, like OpenAI's original GPT from back in 2018, they had a clever idea. But, and this is a big but, when they tried to make it bigger, to read, the entire internet, they smacked right into a wall. A really, really big one. So, their approach was based on this thing called byte pair encoding, or BPE for short. And it's actually pretty clever. Imagine you give the AI a giant library of books. It starts by looking at the most common pairs of letters. It sees T and H together all the time, so it's like, okay, let's just make TH its own thing, its own token. Then it sees ing everywhere and does the same thing. It just keeps merging the most frequent pairs, building up from letters to word chunks and eventually the whole words. It's basically letting the text itself create its own dictionary. Pretty smart, right? But, and here's the big catch, for this to work universally, the model's starting alphabet had to include every single character you could possibly type. We're talking about the entire Unicode set. That's every letter, every accent mark, every symbol from every language, and yup, every single emoji. Everything.
And what does that add up to? Well, you're looking at a starting alphabet of over 130,000 characters. That's before the model even does any of that clever merging we talked about. The GPT-2 paper from 2019 looked at this and basically said, no way. This is just way too big, it's inefficient, and it's a total nightmare if you ever want to build something bigger.
All right, now we get to the breakthrough. This is where that 2019 GPT-2 paper comes in and just completely changes the game with a solution that is, well, it's brilliantly simple. The researchers basically took a step back and asked, instead of teaching it every character, what if we taught it the most basic building blocks of digital text itself? And this right here, this is the core idea. The old way, from the 2018 paper, was to start with that massive library of Unicode characters. The new way, the 2019 breakthrough, was to forget all that and just use bytes. The 256 basic units that, underneath it all, make up literally every single thing you see on a screen. I mean, just look at that number, 256. That's it. They went from a clunky, bloated alphabet of over 130,000 characters down to a super elegant universal alphabet of just 256. Because with those 256 bytes, you can perfectly build any text in any language, no exceptions. It's beautiful. So shrinking the alphabet was a huge deal. But they didn't stop there. The next step was to use this new, clean foundation to build a vocabulary that was not just smaller, but way, way smarter. So as they started applying their BPE process on top of these bytes, they noticed something kind of wasteful. The model would see dog followed by a period all the time. And it would create a special token for dog, dot, and another one for dog, exclamation, and another for dog, question mark. Each one was taking up a precious slot in the model's vocabulary. That's just super inefficient. The fix was, again, super simple but so smart, they just added a rule. Don't let the BPE process merge across character types, so don't combine letters with punctuation. That's it. Suddenly dog is its own token, and the period is a separate one. Way cleaner, way more logical. And this quote from the actual 2019 paper just wraps it all up perfectly. This input representation allows us to combine the empirical benefits of word-level LMs with the generality of byte-level approaches. In other words, they got the best of both worlds. They got a model that can think in word-like chunks, which is really powerful, but it's built on a foundation that can handle literally any text you can imagine. Okay, so why does this matter? Why are we geeking out about tokenization? Well, because this one tiny technical change is what blew the doors wide open for everything that came next. It was the key that unlocked massive, massive scale. Well, let's just break down the advantages here. First, universality. The model can now handle any text you throw at it. Zero errors. It never has to see a character and go, whoops, don't know that one. Second, efficiency. That final vocabulary size, a tight 50,257 tokens, super compact. And that leads to the big one, scalability. This lean, efficient foundation is precisely what allowed them to start building bigger and bigger and bigger models.
And you can see the proof right here in the data they published. Look at this chart. As the models get bigger, going from 117 million parameters all the way up to over 1.5 billion, their performance on all these different tasks just goes up in this beautiful, predictable line. That's the magic right there. This smooth scaling, this bigger is better trend, it was all made possible because they solved that fundamental tokenization problem first.
You know, what I love about this whole story is that it shows how sometimes the biggest revolutions don't come from some crazy, complicated new design. They come from finding a simple, elegant solution to a really fundamental problem. And it just makes you wonder, right? What's the next simple idea, hiding in plain sight right now, that's about to change everything all over again?